Hey Wheaton North, Mr. Yergler here. We're going to talk about energy of reactions and look at some phase diagrams, or some energy diagrams I should say. But before we do that, I want to do a little quick review on law of conservation of mass, because you should be pretty comfortable with this by now. If you're not, then you need to make sure you get some extra practice in so that you're good to go. Alright, let's go ahead and balance this equation. You should have coefficients of 2, 3, and 2. Remember that the 2 means that we have 2 atoms of iron, right? And the 3 means we have 3 separate molecules of chlorine. And the 2 here, the subscript of 2, means that there are 2 atoms that make up that molecule, or 2 atoms in that molecule, right? Now, we want to know the mass of the reactants. So I put the molar mass, or the atomic mass, in each circle to represent the atom and its atomic mass, okay? So iron, if you look on the periodic table, has a mass of about 56. Now, when we total up the mass of the reactants, you add all these numbers together, it comes out to 322 grams. If this reaction were to take place and we were going to use up all of these atoms and molecules to make 2 molecules of FeCl3, what would that mass be? Well, where did we get these atoms to make these molecules? We got them from over here. So if we're using all of these molecules and atoms over here to make these molecules over here, then it would have to be the same mass, because mass is neither created nor destroyed. So if you were to add up all those numbers again, you would still get 322. All right, now this is a very important point that some people are still struggling with. The mass of the reactants has to equal the mass of products, okay? Mass in a reaction has to come from somewhere and has to go somewhere, okay? So the mass before is always the same as the mass after. And that's because the number of atoms is the same before and after. All of the atoms that we end up with, we already had at the beginning, okay? We're just rearranging them to make new molecules. This is a point that a lot of people get confused on, though. Number of molecules is not conserved. This makes sense because this is a synthesis reaction, right? We're taking 2 separate things and we're putting them together. So we have 2 molecules over here, and we have 3 molecules and 2 atoms over here. So the number of molecules is not conserved, and that's fine because we're putting 2 molecules together to make bigger molecules. So that's going to make sense. We just kind of assume that those reactions take place and that we can just kind of rearrange those atoms however we want. But let's kind of dig into exactly how these reactions take place. 2 chemicals can only react if they make contact with each other, first of all, and they also have to hit each other with enough energy, hard enough, and with the correct alignment, meaning that they have to be kind of turned the right way, right? So this picture just kind of shows an example. It shows that roughly 1 in 5 reactions in this case are effective, and that's because these ineffective ones are either hitting each other with not enough energy, or they just happen to be turned the wrong way. And so a lot of these are ineffective. Most impacts, most collisions between molecules don't actually make a reaction. Now, when we're creating a reaction, when we're creating a product, we're actually forming new bonds, right? We're breaking bonds and we're forming new bonds to form new molecules that weren't there before. And that's because the valence electrons are kind of being swapped around or shared, or depending on if it's ionic or covalent. All right, now some reactions happen spontaneously. The moment you add the reactants together, the reaction automatically starts happening. Think of like baking soda and vinegar, right? As soon as you pour some vinegar into some baking soda, it immediately starts fizzing. But some reactions, actually most reactions, need some help to get going. Even when they're mixed together, they still don't react, okay? They need more energy in order to get them to have enough energy for their collisions to be able to swap valence electrons. All right. There's 2 ways that we can do this, that we can give reactions some help. We can provide the energy that they need. That's called the activation energy. Or we could add a catalyst. Okay, so let's look at each of these one at a time. Activation energy. The activation energy is, as the name implies, the amount of energy required to activate the reaction. Okay, so we like to use a boulder and a hill analogy here. In order for the rock to end up at the bottom here, we have to first put in a lot of energy to get it up over the hill. Only after we get it up to the peak here will it then go on its own, right? And this is kind of how reactions take place. The activation energy is the amount of energy we need to input in order to get the reaction to follow through or to get carried out. Okay, so no reaction occurs until we get to that point. There's a couple ways we can provide the activation energy. We can provide physical energy. That's like stirring it or shaking it or something like that. We can also provide heat. The third way is electricity. We can also add energy by adding electricity. All right, so that's the first way. We can also make a reaction go forward by adding a catalyst. You might remember from biology that enzymes are kind of like catalysts. They change the environment such that the reaction occurs more easily or more quickly or more efficiently. Okay, so they're not actually a reactant and they're not a product either. They're only changing the environment so that less activation energy is needed. Okay, we have a little picture here to kind of show this. This is like your molecule that wants to break apart. However, it would require a lot of energy to do that. But if the catalyst comes in here, represented by the black dots, the catalyst kind of facilitates the breaking apart of the molecule. Okay, it changes the environment so it's easier for this to break apart. So when you're done, you're left with the catalyst still, and then you have your products. Okay, so a catalyst makes the reaction occur much faster, and it's unaffected by the reaction. A lot of people tend to think that it's kind of like a reactant, but it's not. It's just present when the reaction is taking place, but it's there before the reaction and it's still there after the reaction. Okay, it's not used up. All right, so let's look at some reaction graphs. We're going to use the x-axis on this graph to represent time, or the course of the reaction. So over the course of the reaction, a reaction happens over time. So we're just going to use this kind of generic unitless axis. Okay, and same thing here on the y-axis. We're going to say that these are kilojoules, but we're not going to be picky about how many particular kilojoules we have. We're just going to say the y-axis is energy. All right, so at the start of the reaction would be at time 0, about right here. We're starting it with a certain amount of energy. Okay, these are our reactants. As the reaction takes place, we start producing products at the end, right? This is at the end of the reaction, and this is at the beginning. Now, look at the shape of this graph. Where is there more energy, the reactants or the products? The reactants have more energy because they're higher up on the y-axis, okay? So this is the energy of the reactants, and this is the energy of the products. The energy of the reactants is higher than the energy of the products. If we extend this line, just to kind of see where we were at, how much energy is required to get the reaction to start would be represented by this arrow here. We're starting with this much energy in our reactants, but we need to input a little bit more energy in order to get the reaction to go forward, right? This is what we call our activation energy. You need to be able to recognize that E sub A is activation energy. Now what about this one? This distance here. This is the energy from our products to our reactants. So this is like the difference between the reactants and the products. I'm going to call this the energy of the reaction. This is how much energy was given off, in this case, in the reaction. We started with this much, and we ended up with this much. Okay, so this amount of energy is the energy of the reaction. And you could calculate that if you wanted to. It would be the products minus the reactants. We're not going to get real picky with actually calculating that, but you need to be able to identify that this is the energy of the reaction. Now, how will the graph change if we add activation energy? This means that the activation energy would be higher, so we would require more energy to get up to a higher peak, and then the reaction would go forward. It would not affect the energy of the products, and it wouldn't affect the energy of the reactants. It would only affect the energy of the activation. And what if we had a catalyst? Remember that a catalyst makes the reaction more efficient or faster or easier with less energy, right? So what would this look like if it required less energy to make it go from reactants to products? Well, you would have a smaller hump to get over, right? So you would still have a hump. You still have some activation energy, but maybe it would go about right here, right? A little bit smaller. And remember that the catalyst doesn't affect the reactants, and it doesn't affect the products. Okay. Now there's two different types of reactions, whether they release energy or whether they absorb energy. The picture that I just showed you, the energy in the products is less than the energy in the reactants. So therm meaning heat and exo meaning exit or leave. Heat is leaving, right? We're releasing energy. We're releasing heat or we're releasing light. And this would actually feel hot. An exothermic reaction feels hot because it's releasing energy. There's also an endothermic reaction. This is when reactions absorb energy. So the energy in the products is more than the energy in the reactants. This is kind of the opposite. It's absorbing energy over the course of the reaction. So this would actually feel cold because it's absorbing energy from our hand. Now here's two reactions or two diagrams. I want you to choose which is exo, which is endo. There's one of each here. Not only should you be able to identify it, but you should also be able to explain it. Why do you choose one over the other when it's exothermic or when it's endothermic? Okay. Make sure you have those answers written down and bring them to class so that we can kind of discuss it and so that you can double check whether or not you're right or not. This is Mr. Yergler signing off.